Alright, Rock Ridge High School, Algebra 2. This is day 13, which is the third day of Unit 2. Today we are discussing analytic composition and inverses. So last class we discussed graphical composition and inverses. Today we'll talk about the algebraic or the analytic version. Alright. So to begin with, let's get some vocabulary down. So basic function operations, we need to understand how these things interact with each other. Always remember the domain of a function is all possible x values. All possible x values is the domain of a function. So if you are presented with the algebra of a function here, you need to start to think, what am I not allowed to do for the domain in the real number system, and what am I allowed to do? Remember back in Unit 1 we talked about what the real number systems are. So those are of course not imaginary numbers, right? So if you cause an imaginary number with some kind of input, that's what you're not allowed to do. So we're trying to avoid imaginaries. So things like negative square roots, are not allowed because, again, we're talking about the real number system. Remember, negative square roots, those are imaginary. So any input of a domain, any domain element that causes a negative square root needs to be eliminated from our domain. Also, no zero in the denominator. Zero in the denominator is a problem as well. So any input that would cause a zero in the denominator is something we want to eliminate from the domain as well. So let's look at our first example. F of x equals x squared plus 3x. Is there anything we can input for x? Is there any element of the domain that we could input for x that would cause a negative square root or cause a division by 0? The answer to that is no. We can put everything we want into x, and this will never result in a negative square root or a 0 in the denominator. So we can say the domain of this is all real numbers. Everything we can think of in the real numbers, we can input to this and not cause a problem. Number 2, is there something we can put in for x that would cause one of these scenarios, a negative square root or a 0 in the denominator? Well, there aren't any input values for a denominator here, so we're safe with the division by 0. But a negative square root could definitely be caused. If we were to put any negative number in for x, we would cause a negative square root. So we need to state our domain to make sure that it doesn't include any negative numbers, because we'll cause a negative square root if we input a negative number here. So we need to say the domain is anything where x is greater than or equal to 0. 0's fine, 1's fine, 2's fine, 3's fine, but nothing less than 0 is okay, because that will cause a negative square root. Number 3, let's look at what could possibly go in here to cause one of these problems. Well, we're not dividing by any variables, so we can't put anything in for x that would cause a 0 in the denominator, so we're safe there. But we could cause the square root of a negative with certain values. Well, where does that happen? Where does it happen that we would have the square root of a negative? Or where do we have to force x to be? We know that just like up here, everything under here needs to be greater than 0. We need to have x plus 2 greater than or equal to 0. Otherwise, we're causing a problem. If x plus 2 is less than 0, that's a problem. We'll have a negative square root. That's not a real number. So x plus 2 in here needs to be positive. When does that happen? That happens when, let's subtract 2 from both sides. That happens when x is greater than or equal to negative 2. So that's our domain. The domain is when x is greater than or equal to negative 2. Anything less than negative 2, I will be causing a negative number in here, and I'm not allowed to do that. That'll cause an imaginary. Number 4, we don't have any square roots to contend with here, so we can't possibly cause a negative square root with a specific x value. But there is something that we could cause. We could cause a 0 in the denominator. We could be inputting something in here that could cause a 0 in the denominator. So let's make sure that never happens. Let's make sure x minus 3 is never equal to 0. It can be less than 0, it can be greater than 0, but the thing on the bottom here can never be equal to 0. When does that happen? If we add 3 to both sides, we find that x can never be exactly equal to 3. So the domain is everywhere except when x is equal to 3. That's the domain for this one. We can cause a square root of a negative here. We need to prevent that. So we need to say 3 minus x is greater than or equal to 0. This expression can never be negative, so the whole thing needs to be greater than or equal to 0. When does that happen? Well, if I subtract 3 from both sides, I get negative x is greater than or equal to negative 3. I need to divide by negative 1 on both sides, and when I do that, I switch the direction of my inequality. So x, positive x, is now less than or equal to 3. So the domain of this is when x is less than or equal to 3. If it's any bigger than 3, then I've got a negative in the radical, in the square root. Final example in this section. There's nothing that I could put in for x that would cause the square root of a negative, so I'm safe there. But there is a situation where I could have 0 in the denominator. There's something that I could put in here that would cause a 0 in the denominator, and I need to avoid that. So I figure out what's going on down here. 2x plus 12, you're never allowed to equal 0. Well, for what x value, for what domain value does that happen? Subtract 12 from both sides. 2x does not equal negative 12. Divide 2 on both sides. So we're saying x can never equal negative 6. That's the domain. It can be anything else. It can be everything less than that or greater than that, but it cannot be exactly equal to negative 6 because that would cause a 0 in this denominator. So that's stating the domain of the functions, knowing that there are limitations. Are no square roots of negatives and no division by 0. Let's now see how functions operate together. Let's see what happens when we're asked to add functions together, subtract functions from one another, multiply functions together, and divide functions. Let's see what happens. It probably goes exactly as you would expect. If you see an f of x, you can replace it with what f of x is that they're telling us it is. So we're saying f of x, or 2x to the third, plus g of x, which we're being told is negative 6x to the third. The operations are very similar to what you've seen in other algebra classes. Now we see if there's any like terms to combine. There are. We have 2x to the thirds and negative 6x to the thirds, so we have a total of negative 4x cubed. We've added two functions together. Very similar things happen when we subtract functions. We take that 2x to the third, which is f of x, and we subtract the g of x function, negative 6x to the third. We have some like terms here that we can combine. This becomes 2x to the third plus 6x to the third. These are like terms, and we combine them to be 8x to the third. That's subtraction of the functions. Multiplying the functions together, again, very similar to what you would expect. So we take the f of x function, which is 2x to the third, and we multiply it by the negative 6x to the third. What happens when we do this? When we did expressions, what happens when we did that in the first unit? 2 times negative 6, that's negative 12. X to the third times x to the third. Don't forget what we do with those exponents. When we have base to a power times base to a power, that's x to the sixth. We add them. There's no more simplification or combining we do, so that is f of x times g of x. Division, again, very similar to what you would expect. 2x to the third divided by negative 6x to the third. We can simplify this. An x to the third and an x to the third cancel, or the 3 power subtracts a 3 power, and that becomes 1. And I would like you to simplify this fraction, so negative 1 over 3. So that's function operations. If you have a function and you need to add them together, subtract, multiply, or divide, make sure that you replace the expression f of x with the entire function that it is. All right, last class we did composition of functions graphically. And remember, we worked from the inside out. Well, the similar work is going to be done if we have algebra to work with. We work from the inside out. So if we have the function f of x is 2x plus 2, and the function g of x is 3x minus 1, and we're asked to find the composition f of g of x, don't forget, the inside is where we work first. So we take this to be f of 3x minus 1. Remember, we take the inside and we find what that to be. That is 3x minus 1. So we put that in here. Now we're asked, what is f of 3x minus 1? Well, remember when we were asked things like, what is f of 2? What did we have to do there? We had to plug 2 in to the f function everywhere we saw it, right? So we would say that is just 2 times an input of 2 plus 2. So that's 4 plus 2, that's 6. Very similar thing happens when you're inputting an entire function into the f function. Anywhere we see an x in the f function, we replace it with the whole thing we see here. So we say 2 times 3x minus 1 plus 2. Notice you're not going to get to a nice pretty number like 6. You have x's in here, and that's fine. Your composition of functions can simply be stated with x values in there. All I need you to do is distribute this to, get like terms together, and state your function. So let's do that now. 2 times 3x is 6x. 2 times negative 1 is negative 2, and then plus this 2 on the end. These cancel. So the composition f of g of x ends up being 6x. So these are not going to play out as nice, pretty finished numbers like we had when we had numerical inputs. When we input a function into a function, we'll probably have x's left over. Now let's do it in reverse. Let's do g of f of x. Remember to work from the inside out. So restate this as g of, what is the f function? G of 2x plus 2. G of 2x plus 2 means anytime we see a variable in the g function, we input 2x plus 2. So 3, my input goes here, so 3 times this whole function, 2x plus 2. So we've taken care of the 3x part, and now we have a minus 1. Now distribute and combine like terms. 6x plus 6 minus 1. Last little step here. 6x plus 5. Again, it's not going to be a nice pretty number with these composition of functions, and that's fine. So g of f of x is 6x plus 5. So let's do a couple of these. We're going to do the composition, and then when we're finished, we're going to go check and see what the domain needs to be. So we are inputting the g function into the f function. So let's restate this just by reminding ourselves. This is f of 2x minus 1. All right, if that's the case, I take 2x minus 1 as my input and put it into the f function, and all inputs go here. So that means that's 3 over 2x minus 1. Now, there's nothing else to simplify here. So as far as composition of functions is concerned, we're finished with that step, finding the composition f of g of x. But remember, we were also asked to state the domain. So let's take a look here and see if we've got some limitations. Can we find anywhere where we could cause a square root of a negative? Anywhere in here where we can find the square root of a negative? No, I don't see any square roots, so we can't cause that problem. Can we cause the problem of dividing by 0? Yes, there looks like there's a risk here. So let's go find out how to avoid that. Let's say 2x minus 1 can never equal 0. When does that happen? When 2x does not equal 1, x cannot equal 1/2. So our domain for this is x cannot equal 1/2. It can be less than, it can be greater than, but it cannot equal 1/2. Now we've completed both parts of that. Now let's go in reverse. Let's take g of f of x. Remember to take the entire f of x function, which is 3 over x, and input it into g. So what happens when we do that? Well, when we take 3 over x and replace the inputs of g with that, we get 2 times 3 over x minus 1. We looked at the g function, and anywhere we saw a variable, we input the f function, which is 3 over x. Now we simplify, so we've got a 6 over x minus a 1. So we're finished with our composition. That's our answer to what what g of f of x is. Now let's go find out what's going on with the domain. Can we possibly input something and cause the square root of a negative? No. Can we possibly put in something that could cause division by 0? We sure can. This right here, the bottom of this fraction, cannot be 0. There's really no more work to do like we had in the pink here. Just by stating that x cannot be 0 finishes that job of declaring the domain. Let's do f of x. Again, take it from the inside out. We're going to say f of, what's the f function? It is 3 over x. Okay? If 3 over x is our input, we must now say, put 3 over x into the input of f of x. So we say 3 over x. Well, we know from previous classes that this is the same thing as if you're dividing 3 by a fraction, that's the same thing as taking 3 over 1 and multiplying it by the reciprocal of this fraction. These cancel. So you're left with an x over 1, or just a plain old x. So the composition f of x is x. We've answered that first question. Now let's declare the domain. Is there anywhere in here that we could possibly cause division of 0 or square root of a negative? Well, in our final answer, there isn't. We could put anything in here and not cause any of those, either of those problems. However, back in the beginning of our problem, there was a step in which we could have caused that problem. We could have caused a division by 0. Therefore, we need to go back to all steps of our problem and make sure, or at least this first step here, and make sure that at this stage, there wasn't a way that we could cause a problem. Since there is a way to cause a problem in this first stage, we need to declare the domain to be x is not equal to 0. It can be anything else, it just can't actually be equal to 0 because of this step here. Let's look at g of x. Remember that we input the g function 2x minus 1 as the input into the g function. So let's figure out what that is. 2x minus 1 input into the input here of this function. So 2 times 2x minus 1, that's our variable input, minus 1 is what this becomes. Simplify this out, 4x minus 2 minus 1, or 4x minus 3. That's our final g of x. Is there anything we can do, either in this step or in this last step, that would cause division by 0 or square root of a negative? No, there is not. Therefore, the domain for this is all real numbers. There are no troublemakers here. There's no way we could cause a problem here. Now, f of g of 1. Again, I suggest working inside out, and since the inside of this is not an x, it's an actual number, we can actually figure out what that is. So we're trying to take f of g of 1. Let's figure out what g of 1 is. It's going to be a nice pretty number. G of 1 is when you input 1 here. So 2 times 1 minus 1, or 1. So since g of 1 is 1, we will go take that and input that into the f function, because we're taking f of this. So f of 1 we put 1 in for x here. 3 over 1. We input 1 as x into the f function. So the answer to this is 3. We don't really have much of a domain statement to say here. This is a 3-stepper. Don't panic. Work inside out. First find what g of 2 is. Let's find what g of 2 is. G of 2 happens when we input 2 into the g function. So 2 times 2 minus 1, which is 3. All right, that's the input of that. Now let's look at the next step. We're being asked to find the f of that. So we're asked to find f of g of 2. Well, g of 2 we just said is 3. So what's f of 3? Work inside out. F of 3 means I put 3 over 3 into the f function, which is of course 1. I'm not finished yet because you wanted me to take g of that. So g of f of g of 2, or g of f of 3, that means I put 1 into the g function. So see how I worked inside out? G of 1 is quite simply entering 1 in for x here into the g function. So 2 times 1 minus 1, which is 1. So that is algebraic composition of functions, or analytical composition of functions. Work inside out. Take your time. If the inside of your composition is an x, you will likely have x's in your final answer. If the inside of your composition is a number, you will likely have a number as your final answer. All right, inverses. Remember from last class we looked graphically at inverses. We are now going to look at the algebra of inverses. Now remember what we said. The inverse function is the reflection through or across the line y equal x. And remember what we did. We switched the variables. We swapped x and y. So that will still be our first step here. We will swap x and y. So let's do that first for number 13, just to see how these things go. Let's swap x and y. If I see a y, I make it an x. If I see an x, I make it a y. Everything else is the same. So that's my first step. The second step is I need to solve for y. I can't leave it like this. I need to state my function as a y equals. So I do the steps for that. I add 4 to both sides, so x plus 4 equals 2y. And I divide both sides by 2, so y equals x plus 4 over 2. So that's my second step. I solve for y. My final step is writing my answer in correct notation. And let's talk about what correct notation is. If your function started out as a y function, your inverse function needs to be stated as y to the negative 1 power. Y to the negative 1 power is how we label inverse functions. The inverse of y is stated as y to the negative 1. And we just copy over what this is. Y to the negative 1 is x plus 4 over 2. That's our last step, is to put it in proper notation. So let's see how this plays out on number 14. First decision. For simplicity's sake, let's for right now call this y. Y equals 1/2 x plus 3. So to help us get started, let's go ahead and think of this as a y, so that when we swap the variables, it's a little easier to think about. So swap x and y. So now x equals 1/2 y plus 3. Solve for y. X minus 3 equals 1/2 y. Keep going. Y equals 2 times x minus 3. We've now solved for y. We should now say that the f of x function, or the inverse of the f of x function, f to the negative 1 of x, that's proper notation, is this, 2 times the x minus 3. And we would like you to say that it is 2x minus 6. F to the negative 1 of x, the inverse of f of x, is 2x minus 6. The replacement of f of x with y is really just to simplify the swapping of the x and y step. When you go back and do your part C, your step C, that's when this function notation comes back into play. The same thing will happen for 15. We've got an h of x. I want to think of this as a y equals x squared though, okay? So my first step is to swap x and y. So swap x and y. And what do I do to solve this? I take the square root of both sides, right? Take the square root of this side and the square root of this side. And I say y equals the square root of x. Since we already have x is greater than or equal to 0, I don't have to account for the fact that this is plus and minus. Since this says x is only greater than or equal to 0. Oh, I apologize. Yes, we need to take care of this. And we need to also say this is the all real numbers, right? X is greater than or equal to 0, so this is all real numbers. We're not having any imaginaries in here. All right, so we've swapped x and y. We've solved for y. Y equals the positive and negative square root of x. And now we need to go back into the original function notation and declare h to the negative 1 of x, or the inverse of h of x, is the positive and negative square root of x. That's your final step on that. G of x, let's help ourselves out again. Let's make this y equals the square root of x plus 2 for swapping purposes. And let's do that swap. So x equals the square root of y plus 2. How are we going to get y by itself? Well, we talked about how this happens back in our last unit, when we were solving in our last unit. How do we start digging y out of here to get it by itself? What do? We raise both sides to the 2 power. We raise both sides to the 2 power. That's the only way to start digging y out of this mess. Now we can subtract the 2 from both sides and get x squared minus 2 equals y. Now, for our final step, let's go back and check to see what our original function was. Our original function was g of x, so we now declare that the inverse of g of x, g to the negative 1 of x, is this x squared minus 2. So we're bringing into play our lessons from Unit 1 for solving these. 17, this is a gimme. This is going back to last unit. You're simply swapping x and y. There's no solving to do here, right? Just swap it. So go ahead and declare the inverse to be negative 2 comma 5, 3 comma 6, and negative 4 comma 9. That's the inverse of that relation. All right, enough of this easy stuff. Let's go back to what we were doing. H of x. Let's go ahead and call h of x y for purposes of solving and swapping. So now let's swap this. Let's say now x equals y cubed plus 2. Let's go back to our first unit and think, how do we dig y out of this? Well, we subtract 2 from both sides to get x minus 2 equals y cubed. How do we get y by itself? Well, we remember this from last unit. Raise both sides to the 1/3 power. So we now can say y equals the cube root of x minus 2. But wait, that's not how we started with. We didn't start with y's, we started with h's. So let's put this in proper notation. The inverse of the h function is the cube root of x minus 2. Remember your steps. Swap x and y, solve for y, and then check to make sure you have the proper notation in the end. Your answer is not complete if you only complete the first step of swapping x and y. You cannot leave it at these first stages of where x and y is swapped. You must solve for y. Remember your Unit 1 steps of solving for y. All right, verifying the inverse. When we take these inverses, as we just went through this page of finding these inverses, we actually have a step where we can verify that they are the inverses of each other. Functions f and g are inverses if and only if the composition f of g of x equals the composition g of f of x, and both of them equal x. So this is a check we will need to do for ourselves sometimes. If we were ever asked to verify or determine if the following pairs are inverses of each other, we must first find what the compositions are. So f of g of x, we know how to do this. F of the function 2x minus 4. Well, f of 2x minus 4, that means I take this and I input it into the f function. So 1/2 times 2x minus 4 plus 2, what does that equal? 1/2 of this is x, 1/2 of that is negative 2 plus 2. Those cancel, that equals x. So we are off to a good start. F of g of x does in fact equal x. But we also must see that g of f of x also does so. So let's do it in the reverse. G of the f function, 1/2 x plus 2. What is that? That means I take this whole function and I input it into g. So 2 times 1/2 x plus 2 minus 4. That's inputting the f function into g. Let's simplify this. 2 times 1/2, that's one of them, 1x, plus 4 minus 4. These cancel. Sure enough, they both equal x, and therefore they equal each other. So I have verified that they are inverses of each other, that this f of x and this g of x are inverses of each other. Let's try number 7. F of, let me put the g of x function in there, negative 3x plus 9 is what I need to check first. So let's put negative 3x plus 9 into the f function. Just looking at these, as a reasonable person, 3x minus 9 and negative 3x plus 9, they sure do sound like inverses of each other. But let's check and see if they are. Negative 3x plus 9. Let's input it into this function. 3 times negative 3x plus 9 minus 9. Let's see what that equals. Well, I've got a negative 9x and a 27. Hold on a minute here. F of g of x, if I put you in here, negative 3x plus 9 minus 9, I've got negative 9x plus 27 minus 9. That doesn't look like x to me. Okay, that doesn't look like x to me. If this is not x, if f of g of x is not x, I can stop working. This doesn't simplify down to x. So these are not inverses of each other. Even though a reasonable person looking at these, sure, that looks like they could be inverses. But when we took the composition, it did not equal x. And so we can actually stop after that first step. Don't forget, graphs of inverses are reflections through y equal x. And I think we did this in our last lesson. You can redo this exercise and look at our last lesson to see if you've done it right, but you should see the graph of these lines reflected across this line. All right, go ahead and try your independent practice.